Greetings and welcome to your recording for the week of December 5th. We're also in week 16. Just a reminder to make sure that you've got your math notebook out and you're ready to take good notes. You will need to turn your notes in to get credit for your notes this week, so make sure you're taking notes in both this recording as you're watching the recording and as you go through the Schoology lesson. So you will need to submit your notes from both the Schoology lessons and from this weekly recording. All right, so let's start with a little warm-up question about an exponential function. We're going to keep on the theme of exponential functions this week. So let's review some stuff about exponential functions. So first, looking at this function, f of x equals 6 times 0.9 to the x, I want you to tell me if this is an exponential function. So I'm going to let you know it is an exponential function, but does it show exponential growth or exponential decay? And how do you know? And then what is the initial amount? What is the starting point? So go ahead and click pause and try to answer those questions on your own. Remember, trying some problems on your own first. You're going to get a lot more out of these recordings than if you don't. So actually actively participating and trying problems, you will get more out of this. So go ahead and click pause, and then when you're ready to check your work with mine, go ahead and click play. All right, so how can we tell if something is showing exponential growth or decay? So we want to focus on the number that is attached to the x, our x exponent. So 0.9 is our base, x is our exponent. So this is the number that we want to focus on. And because this number is less than 1, we know that this exponential function is showing decay. And we know that because this term here is less than 1. So we can say our b term. Remember, when we have exponential functions, we always say it's in the general format of a times b to the x. So it's showing decay because our b term is less than 1. It's greater than 0, but less than 1. So we know it's showing decay. And then what is the initial amount? What did we start with? So the initial amount, remember, is always our a term. So our a term is going to show us the initial amount. And that means this term right here. So 6 is the initial amount. Is the initial amount. 6 is the initial amount. All right. And then 0.9 is the amount that we're increasing each time. So I'm going to go on to the next slide. We've answered all of our questions for the warm-up, so let's go ahead and talk about some reminders. We are about 2 weeks away from the last day of the semester, something even cooler, actual day count. We are 13 days, and this is from December 5th, so this is from December 5th, this recording. So as of December 5th, we are 13 days out from the end of the semester. So that's important to know just for those of you who are keeping track of how much time you have left, especially if you're trying to hit a goal grade or maybe you've got some outstanding assignments that you still need to get in. So just keep that in mind that we're about 13 days till the end of the semester. It's getting close. It's getting close, guys. So this week, what are we going to do? We're going to look at some compound interest questions. And then we're going to look at writing exponential functions rules from a table and linear and nonlinear rates of change. So let's start with some compound interest. So compound interest is a formula that we can use to calculate the amount of money that you can earn when you deposit money into an account that earns interest over time. So if you put money into an account where you earn interest over time, we can use a compound interest formula to help us determine how much money we can earn over time. So the formula that we're going to use is going to look very similar to the exponential growth and decay functions you've seen so far. So the formula that we're going to use is, let me put this up here, B equals P1 plus R. So remember, for exponential growth or decay, we did 1 plus R as well, right? And then instead of having an X as our exponent, we're going to have T for time. So let's go over what all these variables represents. So B is the balance, the amount that you'll have in your account. So B is the balance. P is the initial amount that you put into the account. Or your principal. Then we've got R, which represents the rate. And remember, this is a really important part. The rate's always going to be given to you as a percentage, but you have to insert it into this formula as a decimal. So it has to be changed from a percentage into a decimal in order to use this formula properly. So that's a really, really important piece here, is that the rate has to go from a percentage to a decimal, and we practiced that last week. And then T is going to represent the time in years. It's going to represent the time in years. So let's do a quick practice problem with compound interest. All right, so here's a type of problem where you can actually use the compound interest formula, where it's, we've got interest compounded annually. That means compounded yearly. So this formula only works when we're looking at the amount of money that we can make when we've got money deposited into an account that has interest that's compounded annually per year. So let's take a look at this type of problem. So you've got $200 and you're going to put that money into a savings account. And that account is going to earn 3% interest compounded annually, yearly. Remember, annually means yearly. So we want to find out what is the account balance after 2 years, and then what is the interest earned. And that just means how much money did you make on that account? What was the interest that you earned? So let's do some math. Let's use that formula. So let's write down what our formula is. That's always your starting point, is what is the formula that we're going to use. So the balance, or the amount that we're going to earn, is equal to the amount we put in, the principal, 1 times 1 plus the rate. Remember, the rate is always as a decimal, and then the amount of time in years. So the amount that we put in is $200. That's our principal. 1 plus, maybe we should write out the variables over here on the side first before we put them into the formula. So the principal, the amount that we put in is $200. The rate is 3%, but remember, we have to insert that as a decimal. So to go to a decimal, we move our decimal 2 places to the left. So it's, if we have 3%, that's 2 decimal places to the left, so that becomes 0.03. So our rate is going to be 0.03. Then the time in years is 2 years. So let's keep plugging in. 200 we started with, 1 plus 0.03, and then we're going to raise it to the second power. So I'm going to go through and clean this up. I'm going to add together what's in the parentheses, 1 plus 0.03. And then I'm going to grab my calculator to help me do the math. So remember, order of operation tells us that we have to do our exponent part first. So remember, order is very, very important here. The first thing we want to do is take 1.03 to the second power. We don't want to multiply these two terms. If we do that first, we're not going to get the right answer. So the first thing we're going to do is type into our calculator 1.03 to the second power. And when I do that, I get 200, we still have that, and I get 1.0609. Now I can multiply that times 200, And I get my balance, which is $212.18. So now I've got $212.18 in my account. So remember, this is a savings account. I haven't touched the money. I'm just letting it sit there and make some money over time. So how much, so this is our balance after 2 years would be that we now have $212.18. That's a little messy. Let me fix that. And then the second question says, what is the interest earned? So to find the interest earned, I'm going to take the amount of money that I now have in my account. So we've got $212.18 and subtract that starting. What did we start with? $200. So how much have we earned over time, over those 2 years? So $212.18 minus 200 is $12.18. So we've earned $12.18 in this account. So the bigger your interest rate and the longer your money stays in, the more money you're going to earn, right? The more interest you're going to earn. Yep. So again, this formula should look very similar to you after doing exponential growth and decay last week, but we're just changing what the values represent. All right, so moving on to, we already did a little bit of review of exponential functions, but just really quick to review exponential functions. We've got the general formula of exponential functions, where A is our initial amount, B is our base, right? The amount that, or the rate at which we are either growing or decaying. The B term, remember, always has to be not equal to 0 or not equal to 1. It cannot be equal to 1. A cannot be equal to 0. And B has to be, I guess for exponential functions, it has to be greater than 0. It has to be greater than 0. It has to be greater than 0. I was going to go somewhere else with that, so I kind of, that might have sounded confusing. Let me start over again. So in our general formula for exponential functions, we have this format, f of x equals a, which is always our initial amount, b, that's the rate at which we grow or decay, and it's always, it's always raised to the x power. The a term is always our initial amount. It can never be 0. And then b always has to be greater than 0. Remember, it can be a fraction, and it can be any number greater than 0, any real number greater than 0. And b cannot equal 1 also. So those are our stipulations there. Remember, when we talked about exponential growth, so if we were talking about exponential growth, that b term had to be greater than 1. If we were talking about decay, that b term is going to be less than 1, but greater than 0. So any type of fraction or decimal, that is our b term. If we have a decimal or fraction, we know that it's going to show exponential decay. And then we talked about the graphs, right? So exponential growth is going to look like that, where exponential decay is going to look more like that. Where exponential growth, our growth starts slowly, but as time moves on, it increases quicker and quicker over time. Same with decay, just in opposite fashion. I'm going to go on to the next slide. So we talked about exponential growth and linear growth and how we can determine that from tables. So I want to review this because it's going to be helpful this week in a couple of your sessions. So linear growth, if we are looking at a table, we can see whether we have linear growth or exponential growth by focusing on the f of x, or sometimes it might be considered your y column. So we want to focus on the f of x or the y column. And what we want to do is look at the change that occurs between our f of x values or our y values. So from 6 to 8, I'm seeing we're increasing by 2. From 8 to 10, I'm increasing by 2. From 10 to 12, I'm increasing by 2. So for linear growth, we're going to see a pattern where you're either adding or subtracting the values in your y or f of x column. So in this column here, we're going to see adding or subtracting. We're either adding or subtracting the same amount every time. Where with exponential growth, remember we're multiplying or dividing as we look down our f of x row or column. I hope I didn't say row over here. I meant column every time. So column, as we look down our f of x column or our y column, we're going to be multiplying or dividing each time. And I meant to say column here too. Now I'm thinking I said row the whole time. I'm sorry. So from 2 to 6, what do we multiply times 2 to get to 6? 3. So we're multiplying times 3. How do we go from 6 to 18? We multiply times 3. From 8 to 54, we're multiplying times 3. So when we show exponential growth in a table, we have a multiple that we're either multiplying or dividing each term by to get to the next term when we talk about our f of x or y values. So that's the big difference here. So you should be able to look at a table and determine right away whether you have exponential growth or or linear growth or decay. It can be linear growth or decay or exponential growth or decay. So now this week we're going to look at how we can write a function rule to show the exponential growth. Or just the exponent, yeah, in this case it's growth, right? We're getting bigger as we look down our f of x column. We're getting bigger every time. How much bigger are we getting? So I kind of already told you that this is showing exponential growth. How much bigger are we getting? So to get from 2 to 6, we multiply by 3, right? Then to go to 6 from 18, we're multiplying by 3. From 18 to 54, we're multiplying by 3, multiplying by 3. So each time we're multiplying by 3. So to find the function rule, the first thing that we want to do is identify the rate of change. And in this case, we're multiplying times 3, right? So that's going to represent in f of x, that's going to represent, or in your f of x equals a times b to the x, that's going to represent your b term, okay? So if we go down here, f of x equals a times b to the x, right? That's how we write exponential functions. So our b term, in this case, the b would equal 3 because we're multiplying times 3 each time. Then the next step is identify the initial value, because remember, a represents the initial value. And that happens when x equals 0. So when x equals 0, that's going to show you your initial value. So your initial value when x equals 0 is f of x is 6. So we've got, in this case, our a is also going to represent the initial value, right? Remember a equals the initial value. So in this chart, the initial value is 6. So now I can just write my exponential function rule. A is the initial value when x equals 0, which is 6. B is the amount or the rate we're increasing every time, which was times 3 to the x. And then we've got a rule. So want to see if this rule works? Want to check this rule out, see if we did it right? Let's do it. So let's say I want to see when my x value is 3, what is my f of x? Or what's my corresponding y value? Let's check it. So if I plug in, if I want to find the f of 3, that's going to be equal to 6 times 3. My x value that I plug in is going to be 3. And then I do the math. Order of operations, 3 to the third, I know is 3 times 3 times 3, which is 27. What is 27 times 6? I'm going to grab my calculator, let it do that work for me, and I get 162, which is what I want to see, right? Because the f of 3 is 162, so we know we wrote this rule correctly. And you'll get to write rules this week. doing just that. So pretty easy, right? Only need to identify two things and understand what each variable represents in the exponential function formula, a times b to the x. And that's why we reviewed this earlier in the recording. A is always our initial value, b is the amount that we are increasing each time, and x stays x. I'm going to go into the next slide where we're going to practice another one. So again, we're getting bigger here. So this table actually represents exponential growth. And I want you to write the function rule, or the function for the exponential growth represented in this table. So if you think you might already be able to do this on your own and you want to try this on your own, go ahead and click pause and try it on your own. Otherwise, I'm going to do this right now. So if you want to try it on your own, click pause now so you don't hear me give the answer, and then you can check your work with mine. Otherwise, here we go. So how do we go? I'm going to choose, so I start with a decimal here. Decimals are kind of hard to work with. So I'm going to move down and see if I can't figure out the pattern without the decimal first. So to go from 1 to 8, that's easy, right? 1 times 8 gives me 8, so I know I multiply 8. Let's see if that pattern still works. 8 times what gives me 64? 8 times 8 gives me 64. That's good. 64 times 8 gives you 512. And then you can check in your calculator, and this does in fact work. 0.125 times 8 is 1. 0.125, and you can check that. Plug it in your calculator. 0.125 times 8, and it will give you 1. So we want to write the exponential function rule. So I'm going to start by writing in the exponential function formula, and we're going to just start substituting in values. So the b in this case now is going to be equal to 3, right? Or I'm sorry, 8 in this case. We're multiplying times 8 each time. What's the initial value? So a is going to represent our initial value. Remember, the initial value occurs when x is equal to 0. So what is that corresponding value when x equals 0? It is 8. Huh, both of our values are 8 here. I didn't really plan that. So now we can just write our rule. So the actual rule would be f of x equals 8 times 8 to the x. That's our rule, and we're done. Pretty easy, right? I've got one more for you guys to practice on the next slide. So I'm going to go on to the next slide, so if you need more time, go ahead and click pause here. So this time, we're actually decreasing. So this would be, let's just say the exponential function here. I don't need to say growth or decay. So write the function for the exponential function. So if you want to try this on your own, go ahead and click pause. Otherwise, I'm going to go ahead and write the rule that represents this table. So now we're going to need smaller each time. So we're dividing, right? We're dividing. So in this case, because we're dividing, this is a little tricky. I should have been showing you guys that the easiest way to find the rate of change, or the amount that we're changing each time, if we look at all these that we did, if we take one of the numbers and divide it by the number previous to it, just like we did with geometric sequences. So if we take like 15 and divide it by 18, we get 3. So if we take a number and divide it by the previous term, so like this case, we would do 25 divided by 125, because that's going to show us the multiple. We never want to say division. We always want to have a multiple. We never want to say, oh, it's divided by. Whoops. We always want to look at what number is being multiplied. So in order to find that really quick, we'll just do 25 divided by 125. So you take a number in the table and divide it by the number previous to it. So when I do that, 25 divided by 125, I get 0.2. So if I do that with 1 divided by 5, I get 0.2. So every time I'm going to get 0.2. That's actually the multiple. That's actually the multiple. So you can check that. So we divided to find out the multiple. Kind of weird, right? But so when you're getting smaller, you don't want to say we divide because that's not, we can't plug it into the formula like that. We have to find what number that we're multiplying every time. So if we're getting smaller, we can find that multiple by taking one number in our table and dividing it by the previous one. So if you use a calculator now, we can check that. So if I say 125 times 0.2, what do you think I'm going to get? We should get 25. 125 times 0.2 is in fact 25. So we always want to look for a multiple, even if we're getting smaller. We want what number when we multiply are we getting, we always want to look for the multiple. So f of x equals a times b. So in this case, what is my a? Remember, the a is the initial amount. A represents the initial amount. What's the initial amount? That always occurs when x is equal to 0. So in this case, our initial amount is 5. What's our b? That's our multiple. That's our 0.2, which we know since we're getting smaller, that's right, because our b term should be less than 1 since we're getting smaller. So put it all together, f of x equals 5 times 0.2 to the x. That's our rule. That's our rule. All right, so that's it. So ready for our key phrase assignment? Let me put that up really quick. Here we go, our key phrase assignment for the week. So we reviewed our function, our exponential function. The general format is f of x equals a times b to the x. And in that, a represents the initial amount, right? We've learned that. We've gone over it a couple times in a couple different formats. The a always represents the initial amount. So in this recording, we looked at how we can write exponential rules from a table. And when we do that, how do we identify the initial amount? How do we identify that a value? How do we identify that when looking at a table? What entry in that table will represent the initial amount? And that's it. So if you need any help with anything this week, let me know. Have a great rest of your week.